had we'll go through this checklist, see if anyone's online. Hello, online chat, can you hear me? I'll try to remember you exist. Anyone out there? Yes, okay, perfect. And we are recording. Okay, so this is your introduction to computer algebra. I just want to introduce who I am. My name is Paul Verbeek. I started working here a couple years ago. I'm teaching the Intro to Software Engineering. I have a PhD in computer science from the University of Western Ontario, where I specialized in computational algebraic geometry, which is basically teaching computers how to deal with like continuous curves, right? Computer algebra is more or less the discipline of explaining to computers how to work with symbols rather than numbers. My master's degree I did at Simon Fraser University, that's in Vancouver. I also did computer algebra, but somehow I got a pure mathematics degree for doing that. And my bachelor's degree is from McMaster University, where I did sort of algebra and computer science at the same time. We don't really have these dual degrees like we do here in Australia. But this subject area is kind of at like the intersection of pure mathematics and computer science, which is like why it's really interesting. In order to do any of this, you really have to do both. And I want to be proof to you that you can sort of be a pure mathematician and a software engineer at the same time. Right? I wouldn't have been able to do any of this work if I first didn't understand how the math worked, and it wouldn't have been good enough for a commercial system unless I was good enough of a software engineer to actually insert it into that commercial system. Okay, so let's go through this Maple demo. So again, this is Maple. It's an older version. I think it's 2020. It doesn't usually look this ugly. I'm kind of old school. I reverted it back to like how it looked like in the 1980s because this is my preference. Normally you would input using 2D input, but I don't really like it. So I'm just telling you this so marketing doesn't come and snap my head off next time they see this. But I'm still going to be able to demonstrate to you the power that's underlying the system because it's really the engine that I care about, not the sort of covering that we put over it. So first thing first, we're going to talk about polynomials, and I'm going to try to convince you that the polynomial in the computer algebra system is the sort of most important atomic object of the system, right? So in numerics, we have floats, and I'm saying that at the very bottom in a computer algebra system is that of a polynomial, right? So this is going to be very important that we can work with polynomials and do so quickly. So it's going to spit up two polynomials here. There's one for F, there's one for G. They pretty print nicely. I don't think you have this in Julia with your pretty printer. But I can do stuff like this, right? It's a sort of this 2D display of polynomials. I can take H, I can expand the product, and I can like simplify these things if I want. Oh, let me try another one and I'll see if I can't get it to simplify it to something better. Okay, this one's simplified by factoring. That was a little bit better. Of course, we can take these polynomials and I can do everything that calculus can do. It's really fun talking about calculus when introducing this system because it's stupidly easy to get derivatives. You just have to tell Maple like the 2 or 3 rules of derivatives and there you go, and it works. What's much harder than getting a derivative are integrals. So this is actually indefinite integral, right? So numerical solvers can only do definite integrals. You have to say, take this sort of polynomial and actually find the area under the curve between 2 and 7, right? This is really giving you the indefinite one. This one's not too hard, right? Because, you know, we could have undergraduates do this type of integral just by, you know, increasing the exponent and multiplying by the appropriate coefficient. But if you wanted to take the integral of this rational polynomial, things may get a little bit more hairy. So like in this system, something like this would be spit out. Now this may look kind of weird, but this is the analytical exact integral of that quotient. It's saying it's x squared over 8 plus x over 8 plus the sum of all of these terms where those r's are roots of that equation down there. And that's why I'm saying like the polynomials are super important in this system, is because we don't really have numbers in a computer algebra system. We have roots of stuff. We don't have the number 1. We have the root of x minus 1. We don't really have the square root of 2. We have the root of x squared minus 2. Does anyone know what these numbers are called? The algebraic numbers. Okay, so our system has extended from integers to rationals to the algebraic numbers. That is any number that is the root any polynomial with integer coefficients. So that gets you a lot more than like a numerical system can do. So numerical system using floats, that basically gets you the rationals, essentially. Whereas here we get, for one, we can represent a fraction properly. 1/3 is already something a numerical system can't represent because you require an infinite amount of threes. And you certainly can't get things like the square root of 2, or going even further, like the root of 7 minus the root of 2 root of 3, something like that. So even fairly more sophisticated algebraic numbers. So stuff like this happens in computer algebra systems all the time, where I'm saying, well, here's your answer. And you may say, but this is like, I actually want an answer. Like, how do I actually generate the integral? And this is sort of the interplay between computer algebra systems and numerics. Like, what good is a numerical system until you have an analytical system that you can build a numerical approximation of? Right. So I'm saying, here's your analytical solution. In order to get roots of this polynomial, do it in whatever way you want. Right. If you want to convert to numerical analysis, just do Newton's iteration or something to pull roots out of that polynomial there. Right. At which point you'd be doing numerical analysis rather than symbolic ones. I'm going to show you that the system can plot because it's like the sexy stuff that marketing likes to pull out. So here's all the plots of the functions that we were talking about before. Right. A lot of them are on the sort of, there's f, there's g, there's h, there's f over g. We can have these nice sort of 3D plots where you get sort of these shaders involved. So it's already pretty cool. You can plot in different coordinate systems. So here's a plot plotted in the cylindrical, spherical coordinate system. That's sort of the infinite sort of spiral twisting into itself. Let's study this one for a second. So usually when you plot something, one of the variables in your equation has to be linear, right? You usually have to say z is equal to this function of x and y, right, to get a plot, because each point is going to be basically the like you have the xy plane, and then you just evaluate z, right, to get your surface. This is a more sophisticated type of equation, right? There is no linear term here. So we can actually still plot these. Like, these will be plots where like things cross over one another. I don't know if many of you have done elliptic curves or anything like that. So we can do implicit plots. This is quite interesting. It doesn't look as nice, but like I can always have Maple like generate a hell of a lot more points to smooth this out. But like, this is one of my favorite features, right? That like we can actually generate plots like implicitly. And this becomes quite important when we want to do things like visually represent the solutions to a system of polynomials, because what does it mean for two polynomials to be in a system which we want to solve? That means we have to find all the points which make both f and g go 0 at the same time, or that is, where do they intersect in space when I draw them? Those are the solutions to that system. Okay, here's a very sexy thing. This is a plot animation of the Bessel function, which is what you, if you hit a drum, the Bessel function sort of represents what would happen if you hit a drum. So, oosh, right, there you go, right? Oohs and ahs, right? Go buy the system. You can actually get this fairly cheap, I think, as students. I think it's only like $80 or something like that. Yes. Is it free through UQ? It'd be great if it was free through UQ. I know you can get Mathematica free because I just downloaded and installed it, but it'd be great if Maple was also free. So I'll have my colleague over there report it. Oh, it's free. So you should definitely, okay, you definitely should download this then, because it's going to be really helpful with your project, because you can use it to generate sort of test sets, right? Because this system is definitely going to give you the correct answer for factoring and multiplying and stuff like that. So you can always compare your results with the ones from this system. I want to show you the graph theory package, because when I was a master's student, the fellow beside me was developing it. And I think it's a really neat thing that's unique to this system. So I'm just going to generate a graph here. And in the graph, I'm just going to say, give me 20 edges that are just like random connections between nodes numbered 1 through 8. So normally, most systems, computer algebra systems or systems that work with graphs, when they draw a graph, will simply make a polygon and put the nodes around the polygon and then connect through the middle, something that looks like this. Now, my colleague came up with this neat idea. He says, instead of doing this, like, why don't we make all of these edges springs? And then we'll just shake it a bunch, and it should stabilize to some type of point. And that's what this does, right? This is what the spring system does. And the idea here is that you just you keep perturbing it until you get something that's nice. Those are kind of ugly. Let's try getting a different random graph. That one's not too bad, right? So this is sort of closer to like what you would draw as a human if you were trying to draw a nice graph. And of course, these export to some stuff that are quite nice. Solving and factoring. Okay, so this is what you need to be interested in, of course, because your project 1 is on factoring. And I want to convince you that factoring is more than just factoring. What you're doing is solving stuff. And solving is really at the root of all sciences, right? You observe something, you come up with some equations that model it, and then normally you want to take those equations and solve it for whatever we mean solve means. So here I have a polynomial out. I'm just going to remove some of this output. Okay, so here I have a polynomial f, and it has roots 1. It has, I think this is the plus minus the cubed root of 3 and the cubed roots of 5. And I'm just going to expand it. If I solve f, like what do you expect this system to report? Or if you're in MATLAB, what would you expect? Or like, what do you think it means to solve something? Yeah, the zeros of f. So there's like an easy one here. So what's like at least one solution that we expect to find here? 1, like one's the giveaway one. So how would you find that in MATLAB if you were to put that in here? I already mentioned the technique, right? Yeah, Newton's iteration, right? You would move along this curve in Newton's iteration and hope to find one of these sort of sync points. But how can you be sure you found all of them? That gets kind of hard, right? These numerical solvers can get kind of ill-conditioned, especially if like roots are close together and stuff like that. So in Maple, in computer algebra systems, you just get them all. And not only do you get them all, you get them exactly. So if we study this, what is it saying the solutions of f are? 1, the cubed root of 3, which is just, it can't, like that's just does not exist in MATLAB. It doesn't have the capacity to represent that. You also get the minus cubed root of 3, the third root of 5, and then these complex solutions, right? There are other cube roots of 5, but it's like when you get the complex ones, right? You have the complex circle and you have to break it by 3. Okay, why should you care about this? Well, how do you think solve works in this system? What it actually did was factor f. And it factored f into this, and it said, there's your first solution. Your other 2 come from here, and your final 3 come from there. Right? So when I teach you how to factor, you have to think, oh, I've actually been taught how to like symbolically solve polynomials, which is like a thing that's a lot more powerful. You probably do know how to factor a little bit. So quadratics you can do, cubics you can do, quartics, there's like a closed form expression. Is there a closed form for quintics? Why not? Yeah, because Galois was like, nah. Do you guys take Galois theory? Oh, so Galois is like a super cool mathematician. If you read about some of the history of these mathematicians, it's like amazing how interesting some of them were. But he was sort of in love with this woman called Colette or something like that. But she was married to his like best friend. So he challenged his best friend to a duel with pistols. But since they were best friends, they couldn't actually like shoot one another. So they had one of the 2 pistols loaded with a bullet, and they like pointed at each other's stomachs, and they like shot each other in the stomach. And Galois just flipped the coin wrong. So the night before the duel, you're sequestered. Like they put you in jail so you can't run away. And during this time, he like wrote down everything that he'd figured out about math on like a single sheet of paper. And from that single sheet of paper, they like derived this entire field of Galois theory. And like the main point of Galois theory, or the main contribution, is that he proved, he didn't, like he just said, there is no closed form for factoring stuff after the quartics. It's just not possible. This also has an equivalency to, you know what straight edge and compass constructions are? Yeah, this has like an equivalent, like it says something also about what angles you can draw with a straight edge and a ruler. Anyway, so that was pretty cool. Okay, so I'm going to give you another function here called g it's x minus 7, x squared minus 3. It looks like this. So now what does it mean to solve two things simultaneously? Well, they're going to say this is the collection of all points that will zero out f and g at the same time. Right? You can think about this if you drew them on the plane. These are the x positions where they're going to sort of cross. Now it's saying it's the root of z squared minus 3. So the other thing that's quite important in computer algebra system is the GCD operation, the thing that comes out of Euclidean algorithm. And the GCD algorithm is going to say f and g have the common factor x squared minus 3. Like, so do you see the relationship between solving something in the GCD, right? The GCD in its generalized form over polynomials is actually doing system solving as well, right? By saying like, these are where the common roots are going to lie, right? So GCDs plus factoring is going to give you system solving, right? So I've shown you how to solve like single polynomials, and now we can solve systems of polynomials. Okay, so this is where we stop on your project. We're only going to deal with univariates. It's going to be tough enough, but I just want to give you like some sense that like it goes well beyond this, right? So of course, the question is, can we generalize beyond the planar case? What about surfaces? And this is where the power of computer algebra systems usually shines. So people use MATLAB. I typically ask this question. Okay, so if I like intersect a circle with a line, you can probably tell me what the solutions are in MATLAB, right? There's two places where they intersect. Okay, let's go one dimension above that. Suppose I give you a sphere and I cut that with a plane. Now what is the solution? It's a circle. So like, how does MATLAB now report back to you that the solution set is a circle? I don't think it can. It can maybe give you some parametric equation, which gives you, like you give it t and it gives you something on that circle. But Maple is really going to be able to say, here's the circle. This is the thing that's the solution to those, to the sphere and to the plane. You get roots out of this whatever way you want, but here they are, all of them symbolically. Okay, so here's a system of equations. I'm going to implicitly plot them. This is why I said implicit plots was one of my favorite things. So they're all the three surfaces plotted in the same region. And to solve this means to like figure out what is the common intersection point in space of these three surfaces. And there are many ways of doing this. Well, at least there's a handful of ways. The main two ways are using Grobner basis and using regular chains. Has anyone encountered Grobner bases yet? Okay, there must not be anyone here from mechatronics. So suppose you have like a robot arm, and the robot arm is given by a set of segments, like with articulation points, right? Like your arm, like shoulder, whatever this is called, whatever that is called. And suppose I'm trying to ask if the robot arm can reach some target and grab something. You can solve that using Grobner bases, right? This is a problem of algebraic geometry. This is called the forward and inverse kinematic problem, right? So this is one of the main practical uses of the computer algebra system is in mechatronics. But again, like you first serve it's like you may have to do a single expensive symbolic computation, but then you take it and then you can do, after that, you do really fast numerical solving of that, right? So it's the whole point here is to use this in concert with numerical systems, not to sort of supplant it. But I'll show you how this works. So this is a fairly recent piece of technology. The algorithm that gives you a Grobner basis is called Buchberger's algorithm. Buchberger's supervisor was called Grobner. And this is kind of odd because Buchberger and Grobner did not get along well at all. But Buchberger did say Grobner was smart enough to give him a good problem, right? So he wanted to honor him, so he called his main accomplishment a Grobner basis. So I'll just do that, and I'll just print them. So do any of you know what an ideal is? Do you know what a vector space is? Okay, so a vector space is sort of like a linear so I give you a set of vectors, and the vector space is a linear combination of those vectors, essentially. An ideal, I give you a collection of polynomials, and the ideal is the polynomial summation of all those polynomials, right? So instead of like adding a bunch of vectors together where you're allowed to put scalars in front of them, you get to add all of these polynomials together and put polynomials in front of them. That's called an ideal. It's sort of similar. In any case, what a Grobner basis is an ideal that's equivalent to this Grobner basis. You know that you can standardize vector spaces, right? There are many vector spaces that generate the same vector space. There are many ideals that generate the same ideal space. And some of these ideals are going to be better than others, right? If I say solve these systems of equations, that's tough. But if I give you these instead, and I say use these to solve the system of equations, why is the second one more preferable to the first one? I'll give you a clue. I'll tell you what the indeterminants of those polynomials are. So what is this? It's a univariate, right? So you can get roots out of that however you want. I don't care, just get them. The next two are polynomials in Z and Y. But if you have a root of Z already, those are just two equations in Y. And then you can solve those two equations in Y to get Y. And then you can put Y and Z into the last one and get your value of X. So the important property here is that of back substitution. You want to be able to isolate one of the variables to get a root, and then you want to be able to carry that up. Okay, we've refined this a bit into something called a regular chain. I was working, so one of these sister laboratories was called ORCA, the Ontario Research Centre for Computer Algebra, and that's where I did my PhD. And one of the things that we were building in ORCA was this regular chains package. And the regular chains package, sort of like I acknowledge that this isn't the best way to like represent the solutions of this system. It may be something that a pure mathematician finds satisfying, but maybe not an engineer. So we took that on and we developed like a different way of solving. It's still based sort of on Grobner techniques, but this is the same system F's. And I'm going to show you what it means to solve it using a regular chain, right? What we call to triangularize the system. That's what we return, right? So a regular chain is kind of like a Grobner basis plus factoring, right? Can we agree that this solution representation is a little bit like more useful than the one previous? They're sort of equivalent. It's just that we did this extra factoring step. So like there's obviously a solution you can read off this, and one you can read here, and one you can read here. And then here's the solution that's like just simply cannot be represented in a numerical system. Because I'm saying you have to grab a root out of this, right? Z squared plus 2Z plus 1 using whatever you want. Like this is how far I can take you with symbolics, right? It's like I'm just saying it's a root of this. Once you get it, Y is like the negative of that root, and then X is like the I guess the root of Z again, right? So this is what we hand over to the numerics people, who then use it to generate sort of float approximations. The big feather in our cap for this laboratory is that when you call solve in Maple, it calls our technology, it calls regular chains, which is a big deal, right? Like when people go, it's fine, don't worry about it, it's okay. You can FaceTime them in if they're interested. Okay, do they have a question perhaps? Yeah. I had to do a little bit of embarrassing to you, but it's okay. But yeah, like solve is like one of the main things people will call when they get into the system. Like this is one of the main reasons to buy Maple. So we really like this. Okay, finally, I wrote this sub package, like this entire sub library of the algebraic geometry tools is my PhD work. And it was twofold, right? So I was asked to, okay, I'll just show you what it does because it takes a little bit of time. Was to add those numbers in front. See this 1, this 2, this 2, and this 2. So what these are, is anyone familiar with like the intersection multiplicity? So when we like some roots or some solutions on curves count more than others. So if you were to intersect a line with a parabola, how many solutions are you expecting to get in total? 2, right? But what happens if you have like a tangent intersection? Well, we count that twice, right? Because it's a tangent intersection. So that's the intersection multiplicity. What if the parabola and the line miss completely? They have complex solutions, right? You just sort of can't see them when you draw it like that. So we had no, this is what, I had to invent these algorithms. Like I really want to explain like why that's different than just implementing it. We had no idea how, period, to calculate these numbers, right? I had to spend 5 years figuring that out. And then once I figured it out, I had to like write the software to do it and do it fast and do it properly. But so this is a really awesome research area to be in, because not many people get to invent algorithms anymore. Most people are just like implementing algorithms, but it's really fun, but like horrifying to be given a problem to say, compute this. We have no idea how to compute it. You have 6 years before your funding runs out. It's good motivation. And I'm happy to say that I did it, and I'm fairly proud. But anyways, this is in the system properly now as a sub package. Since they paid me while doing this pittance while I was studying a PhD, I don't actually see any earnings from this, but I'm still quite happy for it to be there in any case. Anyway, so you should download Maple and give it a try. Okay, so numerical computation. Why do we use it? Well, it's fast and it's extremely well understood, right? There are whole courses here. I'm sure there are many courses in numerical computation that you could take. It's also wholly sufficient to work with numerics, right? NASA only uses 15 digits of pi to navigate like the space. So if it's good enough for interplanetary exploration, it should be good enough for us. 39 digits is adequate to estimate the volume of the known universe, accurate to within a hydrogen nucleus. Like, there really shouldn't be any more reason to like require like hundreds of digits of precision, except for the fact that there's numerical instability. Have any of you ever had to grapple with numerical instability yet? A little bit? Let's talk about this. So I talked about the square root of 2, and in symbolic systems, it's just the root of x squared minus 2, the end, it's exact. However, in any numerical system, you're only ever going to get approximations like you see here on the left, like 1.412. And then when you square it, you don't get quite 2 back, right? You may get 1.99999. You may get 2.0001. So what's this last one? I said you're never going to get 2 back, but isn't that 2? How many zeros does like 2, the exact number, have after it? It has like an infinite amount of zeros. So I acknowledge that this is 2, but it's not 2 point all of the zeros. It's 2 point like some of the zeros. Okay, so there's 2 types of numerical errors that you have to grapple with. It's called absolute error and relative error. Relative error is like how off you are from the exact number as a proportion. So I like to think of working with floats like working with an interval. Right? You have some number and it has some type of like inconsistency, some error. So if you take like an interval and you take another interval and you add those 2 intervals, you now have a new interval which is wider. And if you keep doing that, it keeps widening and widening and widening. So if you were doing science and you said, I measured the person's height, it's 1.2864853 meters plus minus a kilometer. It's like, okay, that's totally useless, right? And like, it's really happy that you gave me all of this precision and then blew it away with all of that error. So one of the main places where we do numerical solving is when doing Gaussian elimination, right? All of science essentially comes down to like linearizing stuff and solving things locally. What do you have to do a lot of in Gaussian elimination? Okay, what do you do in Gaussian elimination? Yeah, additions. It's all it is additions. All you're ever doing at every step is incorporating more and more error, right? So the whole field of numerical analysis is essentially just trying to correct this, like trying to avoid additions by doing multiplications instead. Multiplications are sort of more fine because the errors multiply. And if you have a tiny number and you like square it, it becomes even tinier, right? So all of this, like the fact that I say this precision is fine doesn't mean you automatically get all of the best algorithms. Like the algorithms have to become a lot more refined because you can't just use them in their natural state. Whereas in a symbolic system, you just do it in their natural state because you don't introduce error. Okay, so what are the benefits of symbolic computation? You get arbitrarily large integers, right? Like how big? It's like big period, right? So one of the things you'll be doing in your project is and one of the mistakes we made last year, when it like in an integer in Maple is like something that's arbitrarily big. An integer in Julia is a 64-bit int, and I sort of didn't account for that. So this year you're going to be using big ints, which I do believe are arbitrarily sized ints. So you're going to feel the pleasure of all of these optimizations I'm going to show you. Last year, they didn't get to feel that because they were working not with arbitrary. They were always doing machine arithmetic. We get fractions and we get arithmetic on polynomials, which means essentially we get to work with algebraic numbers. Now, the same thing that happens with precision or accumulating floating point error, there's kind of an analog for this in symbolic systems. Our integers, our fractions get enormous, huge, right? Gigabytes big, right? So we almost sort of generate the exact same problem, but we've actually figured out a way around this. Have any of you heard about the Chinese remainder theorem? This is an extremely powerful technique in this discipline. Are you familiar what it means to count mod something? Oh, this is great. Okay, so I'll just go over it anyways in case someone out there in the YouTube land doesn't. I'm sure all of you are familiar with counting in a residue class, right? Because you could all read off the clock. If I said, so let's have a clock that goes from 1 o'clock to 0 o'clock. We'll just say 12 is 0. You all know if I say 11 o'clock plus 3, that's what, 2 o'clock? Because you went 11, 0, 1, 2. Now, if you have a prime number of hours on that clock, you actually can do division and multiplication on that clock. That's pretty cool, right? So the clock in itself is something called a ring because you get addition and multiplication. If you have a prime number of hours, you end up getting a field, right? Every number becomes invertible. So this is important. Why is this important? Well, this means instead of working with like these huge fractions, if I instead work over a residue class of prime characteristic, we only have to work with like a finitely many integers, which is way faster, right? So I can say, let's figure out the solution mod 5, mod 7, mod 11, 17, 23, and then reassemble these things somehow to get the solution back in the integers. And we do that through this Chinese remainder theorem. So most of you know this, so I'll just repeat myself. This is a technique developed by the Chinese, obviously. And if I tell you that a number is A remainder P, and B, sorry, I screwed this up last year too. If I say that there's a number and its remainder mod P is A and its remainder mod Q is B, Chinese remainder theorem allows you to like recover that original number back N. I wrote an example here. So if I told you that there's a number whose remainder mod 3 is 1, whose remainder mod 5 is 4, whose remainder mod 7 is 6, Chinese remainder theorem allows you to recover the number 34, which is the solution to those three things. And I'm going to show you some results that if we like do enough of these so that the product of these primes exceeds some type of threshold, then we've actually recovered the solution over the integers proper, like the infinite integers. And actually, we can also recover the fraction, which is kind of a miracle. This is called rational reconstruction. The fellow who invented this, have you ever heard the name Borwein? These two are quite famous mathematicians. The one died recently, which was kind of sad. But if you've ever heard that they've calculated some like digit of pi that's like 1 trillion digits down, those are his formulas. The BBP formula is what is used to calculate these digits of prime, the digits of pi, and one of the B's is for Borwein. 2 times in my life has my supervisor died suddenly. So I wouldn't want to supervise me, I guess is the point of that. Okay, so how are we going to use the CRT-based approach for polynomial arithmetic? It's going to become quite powerful when we want to multiply 2 polynomials together. So if I give you the polynomial f and I give you the polynomial g, like we can do it by just taking the leading term of f, multiplying by g, then taking the next leading term of f, multiplying through by g, and adding them all. But it turns out that it's faster to do interpolation, right? So if I give you like, so a parabola is given by 3 points. Right? If I give you 3 points on the plane, there's a unique parabola that goes through that, and you can deduce that parabola through interpolation. So if we think about it like this, if I give you f and g, and I know that f has degree 3 and g has degree 2, I only need 6 evaluation points to then interpolate what their product is. And evaluating f and evaluating g is super fast, right? You just need to do a bunch of like arithmetic on integers. So that's going to be the idea. Take f, take g, find 6 evaluation points, and then interpolate through them. And then we can even interpolate through them in these individual residue classes, right? So you can find these images mod 3, then mod 7, then mod 11, and then like we lift them. Oh, okay, so that's just me describing the interpolation algorithm. So a little bit more about algebraic numbers, because this really becomes important, right? So I'm saying we don't have the square root of 2. What we really have is x squared minus 2. What we don't, like, suppose you want to work with this algebraic number like root of 1 plus cubed root of 7 plus fifth root of 9. Maple can actually give you back like the polynomial that is the smallest polynomial that exists for which that alpha is a root of. So the natural question here is, well, if you're telling me that like all numbers in Maple are represented by polynomials, like how then can we like do basic things like add numbers together or like evaluate things? And I'd say, okay, that's a really good question. We do so by dividing, which this really broke my mind when it was taught to me. Did you know when you divide 2 polynomials, that's equivalent to evaluating the roots of the divisor into the numerator? I know, right? This means that I wasted a lot of time in high school. Okay. Did you guys do synthetic division back in high school where they would say maybe take like x cubed minus 2x plus 2 and divide that through by x minus 3? All you had to do was evaluate the numerator by 3 and it would have given you the answer. Right? So x cubed minus 2x plus 2 divided by x minus 3 is 23. And that's just what you get if you put 3 into f. And not only is that true, this is generically true. Right, so if I want to put into x squared, the roots of x squared minus 2, namely plus minus 2, you just do a division. Right, if I want to put into x squared the complex numbers, I just divide out by x squared plus 1, right, which is the minimal polynomial for I. Right, so this is mind-blowing, right, and very important. The fact that division of polynomials is equivalent to evaluating the roots of the divisor into the numerator. Okay, so we don't really write rem, although sort of more descriptive of what it's doing. We write modulo. Are you familiar with this terminology? Okay, so I'm saying x cubed minus 2x plus 3 is congruent to 23 mod x minus 3, right? Because we're taking all of the roots of this and we're evaluating them here, right? So this is how we end up doing arithmetic with algebraic numbers, right? By just doing division. I want to talk to you a little bit about project 1 before I sort of run out of time, and then I'll just fill at the end with, you know, the remaining 50 slides that I have left over here. But the principal object is the polynomial, yeah? So you're going to have to put a lot of focus into like encoding the polynomial in your Julia project. And the way that it's there currently, it uses this dense representation of a polynomial. So this is how a dense representation of this polynomial looks like, right? So if you have 6x to the 5 plus 5x to the 4, all the way down to 1x to the 0, a natural way of implementing this is just to have a vector. And you put in at position k, the coefficient corresponding to the x to the k plus 1. Don't forget that we are indexing from 1 in Julia. This is really useful because if you want to add 2 polynomials together, it just basically becomes vector addition, which is really fast. Of course, we have to pad the smaller vector with zeros, but still, right? There are lots of advantages to storing polynomials in their dense way. It's not the whole story. Yanni talked to you a little bit about this yesterday. In this dense version that you currently have, we're not putting a vector of only the coefficients. We're putting a vector of terms, which is a little bit unnatural, but it's because you're going to be using, this is going to be helpful ultimately. We didn't want you to also have to develop the term structure in addition to generating the polynomial structure. And it's part of the project to be like, oh, this is a really bad way of doing it. I'm going to improve it. So this is how that polynomial from the previous page would look in your project at the moment. It'd be a vector of terms that look like this, where the kth position holds the term of degree k minus 1. So the third position here holds the term of degree 2. Like this is going to be extremely wasteful, right? Because it represents 0 terms, and there may be tons of 0 terms. In fact, when we do factoring, this is called the cyclotonic polynomial, and these cyclotonic polynomials are going to be very, very important to us when we're factoring. Okay, so this polynomial representation isn't going to cut it for our purposes. Although I do want to say there are situations where you do want to do dense representation. What would be best in this situation and what you should do is have a sparse representation. Don't represent the zeros in your list. The relevant operation for a sparse polynomial is that you want to be able to pull out the leading term fast. You want a constant term access to the leading term. All operations like addition, multiplication, and division will amount to iteratively finding the leading term of a polynomial. So what you want to do is have some type of ordered list where you either, this is up to you. What I'd recommend is implement a heap. A heap is exactly the type of structure that you require in this instance. Are any of you familiar with a heap? You can look it up, but essentially it's something, well, it's a data structure that allows you to work in a array, and it allows you to get the largest thing out in constant time, and it allows you to insert new terms in log n time, because it sort of like stores things as a tree, despite having like a 1D representation. But you can give this some thought. And so this is a little bit of a shove that I wanted to give you in the right direction of like how you should start manipulating your polynomial structure to be sparse. So again, just make sure whatever design decision you make, you're going to be able to get the leading term in constant time. Like that has to be fast. You don't want to be scanning your list to find the leading term. If you had like an unordered list of elements here, that would be kind of disastrous. Like you want to maintain some type of sort so that either the leading term is the very first thing or the very last thing. Okay, so we have 10 minutes left. You have two options. I can go into much more detail about my dissertation, or I can give you like a history of computer algebra from like its inception. Which would you prefer? Okay, I'm just going to go in order anyways. If you want to hear more about this, go to last year's video where I do talk about my contribution a lot more. You can also feel free to download my dissertation. I wrote it like a textbook. Like I really wrote it as like at the entry point into my discipline. One of the things that I really had to grapple with was that there was no starting point. Like they handed me a bunch of 5 papers and they said, you have to understand these 5 papers sort of simultaneously before you can get into this discipline, right? So a lot of that dissertation should be able to be understandable by you. Oh, so I have the benefit of having a really unique last name. So if you just search Paul Verbeek dissertation, I'm sure you should be able to find it. It's on the UWO's or University of Western Ontario's library. Okay, so history of a software. So to summarize the differences between numerical and symbolic computation, on the left here, we'd represent the square root of 2 as that float. You would square it, you get something off, and arithmetic is just float arithmetic. On the right, to get the square root of 2, you'd represent that as the root of a squared minus 2, and you do arithmetic by undertaking divisions. Here's the Chebyshev polynomial. It's a good example because it's like something symbolic, right? The Chebyshev polynomial is given recursively by this kth term here, and it's 2x times the previous Chebyshev polynomial minus the previous Chebyshev polynomial. And like you really can't do this numerically, right? Because you need to build up like a polynomial, right? So if I asked Fortran to give me the Chebyshev polynomial, it can't. Like the best Fortran can do is like evaluate the Chebyshev polynomial for some given input. Okay, so like what's the first system that actually was able to like give me a Chebyshev polynomial? Well, that was Altran. So this was the algebraic translator. It was developed at Bell Labs. A lot of these guys who worked at Bell Labs ended up being people I worked with, like the people who taught me. It's a very small research area. I know most of these people. It was an extension to Fortran, and it provided rational algebra and fractions. And this really did allow you to like introduce a symbol into the system. So it was the first sort of programming language that was able to generate Chebyshev polynomials. Does this cartoon still exist? Probably not. This was like the first webcomic, but it was like so predates webcomics that it was printed in the newspaper. So it's this sort of the younger kid cutting out fortune cookies, but it's all Fortran code. So they're like Fortran cookies instead of fortune cookies. So I thought that was funny. Lisp, has anyone dealt with Lisp before? Oh my God, brackets everywhere. But we sort of like, this was sort of the first computer algebra system or symbolic system by accident. Like, because everything was described in this prefix notation or Polish notation, if you just pretended that indeterminate existed there, you could see this as basically being a polynomial if you wanted to. That's John McCarthy there, and he developed this at MIT. So then there was like a bunch more of this development that happened through the 60s. You get Saint, which is written at MIT. It also used Lisp. It used heuristics to do integrals, and it was about as good as a calculus student, and which is fair, because like that's all a calculus student does when trying to do an integral. Like, you've all taken calculus. Like, what have we told you? We said, oh, try this. If it doesn't work, then try integration by parts. If that doesn't work, try partial fractions. It's like you're just doing a bunch of heuristics. So Saint basically duplicated that. And then they built Formac. Then they built this polynomial manipulator. They being MIT and IBM, sort of going between MIT, IBM, and Bell Labs. In 1965, this math lab was written, not to be confused with MATLAB. And here we really get most of like the modern features of a computer algebra system. Like, simplification was pretty important, substitution, factorization, which is what we're going to talk about, differentiation, which is not that hard, but indefinite integration certainly is. You could start solving ODEs and doing like matrix inversion and stuff like that. In 1966, they convened the first international conference. Like, they assembled all of the Avengers, right, and talked in a single place about computer algebra systems. The development continued in the 60s, so we get Sign, Symbolic integrator, which uses an algorithm to integrate now instead of a heuristic. This is important, right, because an algorithm is much different than a heuristic. You're going to get an integral in this case. You may have to wait a super long time, but you're going to get it. This was one of the things that we were thinking about teaching in this course as part of this unit, how to do symbolic integration. But in all honesty, it's not overly interesting. If you want to look it up, you require something called a Riesz structure theorem. But essentially what we do is we take anything you give us, and we do like a really huge partial fraction. We do all of those integrals, which ends up being logs of stuff, and then we simplify those logs back. Right, so that's the process by which we do integration by algorithm. Reduce, which is still quite popular, was developed at Stanford. That's the original paper. It was using Lisp. So again, brackets, brackets, brackets. These are some of the fellows who developed it. So when I became a graduate student and I met Keith Geddes, who was in a future slide, I was a little bit boozed up at the time, and I said, I assumed you were dead. Right, because I was like a mathematician, and like every single person I was studying from was long, long dead. Right. So by the time I actually started studying like at the cutting edge of the discipline, I started meeting people whose books I read who were alive. And like this was quite shocking to me. Right. So many of these people were alive. This grumpy fellow up front is Tony Hirth. He developed Lisp. I think he's grumpy from dealing with all of those brackets. Let's just skip over the 60s and 70s. These were just people trying to carve out their own niche. What really happened that was interesting is when the 80s happened. So everyone heard of the University of Waterloo? It's one of the best universities in Canada. It's probably one of the best universities in the world for doing math. Like they're one of two universities where you can actually get a bachelor's of mathematics, like not a bachelor's of science with a specialization in math, but a B math proper. Okay, which is funny for me to then say they couldn't afford Maxima, which was like the top of the line software at that point. So we're going to get back to it. So they started thinking, if we can't really afford it, maybe we should build our own. And then the 80s come and they build the first two computer algebra systems based on C, right? This is the commercialization type of era, right? During the 80s, everyone wants to make money. So the two main systems that came out of the 80s was Maple and Wolfram Alpha, right? So I'm sure you've heard of Wolfram. So this is Mathematica. It was developed by Wolfram and gang. It's very much like Maple. We have a sort of friendly rivalry back and forth. We go to the same conference every year called Isaac. In fact, I met Stephen Wolfram. I didn't act surprised that he was alive, and you better by that point. But I took this picture, actually. I was sitting in the audience. To the left is Michael Monaghan. He was my master's supervisor. So it's pretty neat that I got to meet Wolfram. I think he was probably the most famous mathematician that I've met so far. Oh, I've also met Terence Tao. Well, it's up to you then to figure out who is the most famous mathematician I've met. But Wolfram's a really cool guy. Like he quit college because he thought it was boring and awful. But then he just was like awarded a PhD from Caltech because he was so smart. And the thing that impressed me the most is that Richard Feynman sat on his thesis committee, and Feynman is like my hero. So I thought that was pretty neat. Maple was developed by this SCG group, Symbolic Computation Group, another one of these sister labs that I was involved in. And again, it came out of necessity. They could not afford Maxima, so they developed their own computer algebra system that ended up exceeding the capabilities of Maxima. That's Keith Geddes, the fellow I registered my surprise that he was still alive. He's the nicest guy ever. He worked with this individual, Gaston Gonnet. So both of them were the ones who developed Maple. But the other thing that they did, which is kind of interesting, was digitize the dictionary. So, well, someone had to be the first one to do these things, and it was Waterloo is the university that gets to say that the ones who digitized the dictionary. I'd be remiss not to mention that there's a homegrown computer algebra system called Magma. It's not that widely used because it's like super expensive. It used to be under. I don't even think we can get this software for free here. So you should give that a go, though. It's quite powerful. So throughout the 90s, people just made like individual pieces of software trying to carve out a niche, right? We're never going to beat the commercial systems of maybe I can beat them at like simply doing Lie algebras or something like that. And the modern era is all about open source systems. So this is probably the fullest featured open source system. It's called Sage, developed by William Stein at the University of Washington. He came to one of the SCG groups and tried to like spruik his computer algebra system, which was not a great idea, talking to the people who are the ones developing the commercial systems, because all of the things he was trying to impress us with really fell flat. But good on him for trying. SymPy is the open source system in Python. If you're interested in doing projects with me, I actually want to make SymPy as powerful as Maple now. I like no longer work for Maple, like we're still very friendly. I actually prefer open source systems to closed sourced ones. I know how Maple works. I want to make SymPy work as fast as that. I was surprised how underfeatured this was. For instance, it doesn't implement sparse polynomial arithmetic, which was just like mind-boggling to me. And then finally, MATLAB actually, pardon me? Oh, I like Python. I want to do everything in Python. Okay, well, I can look at both. I don't know, maybe I'm a little bit aggrieved by Dr. Stein or something like that, but I'll take a look. I think SymPy is like lower hanging fruit at the moment because a lot hasn't been done in it, and I'm pretty. So this is written in Python as well. The syntax is pretty much Python. Oh yeah, that's like when they told me to learn Julia because it's basically Python. Then it's not basically Python. Okay, in any case, MATLAB has this their math toolbox now. They're also trying to add symbolics to the system. I was very nearly hired by these people, but I refused to move to Germany because I can't speak German. So they kept trying to find me like a lab that I could work at, you know, in Europe and then in Boston. It just didn't end up working out. But symbolic solvers are available in MATLAB. Okay, so next week we're going to start talking about like the actual mathematics required for doing everything that you need. It's pretty interesting, but it's not going to be overly easy. So if you don't have some background, if you don't know what it means to be invertible in a field, I really do encourage you to watch some of the preamble videos. It should help. But the algorithm I'm going to teach you is a pretty modern algorithm for factoring, and it's fairly brilliant. So it's going to be really interesting, but it's going to hopefully my mind will be sharper by then because I'm going to need it. So it's nice talking with you, and I'll see you 3 hours next week. Bye, chat. Oh, they're already gone. I say bye just to see if they're actually here or not, but by the end of class, it doesn't seem like they were. Oh, they're right there.